Welcome to this topology session. Now my pleasure to introduce the next speaker, Bernardo Uribe. So Bernardo got his doctoral degree from the University of Wisconsin at Madison in the United States in 2002. And some years later, among his many awards, he got a von Humboldt fellowship to carry out research at the University of Bonn in Germany. Now he's professor at the Universidad del Norte in Barranquilla, Colombia, and he's the current president of the Colombian Mathematical Society. He will talk about evenness conjecture in equivariant unitary bordism.
So, Mario, thank you very much for the presentation. Thank you very much, everybody, for having come here to listen to this story. So, I came to this question or to this conjecture through a different path than the standard one. And what I will try to somehow tell you in these 45 minutes is that there is a very interesting problem that is old in some sense, related to manifolds and group actions that I think is worth reminding it because it was somehow set up many years ago, and that perhaps with the tools of today and the new ideas we are able to solve them. So what is here is equivariant because we have groups around. Unitary means that there is some complex structure somewhere around. And bordism, which is telling us that we are dealing with manifolds with boundary. So this is what is on top of there. So let me tell you the route that I will take in this talk. I will briefly explain equivariant unitary bordism. And please simply take the idea that I'm going to explain. Everything that I will say here has a geometrical counterpart that I will tell you, and all the symbols that appear there will have a geometrical life. So don't get somehow scared for the symbology. Then I'll explain what the conjecture is, which is in bordism, and I will take some interlude to go and talk on a very simple thing on the composition and representations that I will need to propose or to give some decomposition in K-theory whenever the action is of a certain kind. Then I'll go back to bordism and I will tell you how this information and representations are useful in understanding the bordism of certain actions. I will give some examples and applications with the specific groups, and I will finish with some conclusions. So this is the route that I will take. So again, all this symbology, I'm going to explain it in words. So G is going to be always a compact Lie group, and I will tell you when it will become a finite group. M is always a compact manifold, it may be with boundary, and G will be acting on M differentiably. So unitary amounts, so this word unitary amounts to somehow trying to do manifolds with boundary on which you may endow them somehow with a complex structure. So since complex manifolds are even dimensional and you cannot do somehow a bordism between two of them that makes sense complexly, so what we'll do is instead of endowing the manifold with a complex structure itself, we will make it what is called stable. That means I take the tangent bundle and I may add copies of the reals until I can make that bundle complex. So in that sense is what is called a manifold of such kind is called stably, I mean you have to somehow put copies of the reals almost complex. And so those are the manifolds that I will think of, but you somehow could disregard this structure and simply look for a manifold. So we say that two manifolds are cobordant if you can simply put one here and the other there, and you can put a manifold with one dimension more with the same structure in between. Namely that the union of the two, one with different complex structure, is the boundary of a manifold of that one dimension one. So it's easier to understand it pictorially. Of course, this drawing perhaps is too simple for what I'm talking about here, but you get the idea. So we're thinking manifolds M1, and we say that the manifold M1 and the manifold M2 somehow are in the same equivalence class if you can put a manifold of one dimension more that goes from one to the other smoothly. Dependently on the decoration you put, one can put it that the manifolds are oriented, that the manifolds are unoriented, that the manifold have a stable complex structure, you need to fiddle around with this minus sign that I put on N2. Now, you can also do these sort of bordisms in a target space, and that's somehow the picture on the right. So I can also do bordisms on a specific universe instead of just thinking of them separately. So this is somehow the picture, and you can imagine, so if you're thinking only on manifolds, one-dimensional manifolds, so this is just a copies of circles, union of circles, then you know that as many circles as you may take, you can always bound them. So if you think of the bordism group of one-dimensional manifolds, it's always zero, or like, namely, all possible one-dimensional manifolds are bound, are possible to be bounded. Two-dimensional manifolds, if it's oriented manifolds, you know that there are Riemann surfaces, and we can fill them, so they are all trivial in this sense. But if it's non-oriented, then RP2 cannot be filled. So RP2 just somehow generates the unoriented bordism group of dimension 2. Dimension 3 manifolds that are oriented, this is a very famous theorem of Rochlin, could be they all bound. Any three-dimensional manifold that is compact and without boundary, there is another manifold whose boundary is that one, unoriented or oriented. For four-dimensional manifolds, the CP2 and so on. But in this case, I'm putting it with a little bit extra structure, which is this stably structure. So let me continue. So what I'll do is I'll take these manifolds, we have an action of G, and I will, that have a stably unitary complex structure, and I take the equivalence class which is given by bordism, and I simply call this as a set with this letter. So this means n-dimensional manifold with a G action, mod out by the equivalence classes of this bordism. And I can give this group structure by putting the disjoint union. As we had before, I had a circle, I could add another circle, or 3 circles, or 4 circles, and the operation, the additive operation is just disjoint union. And I could put them all together, all the zero-dimensional, one-dimensional, two-dimensional, and this is what I put here, or here, is the bordism group of unitary manifolds with an action of G. But this group is more than a group. You can make it a ring. You simply take a manifold and simply do the cross product with another manifold which has an action, and you simply take the diagonal action. So that means that you can multiply in this universe, and it's coherent with the grading. The point is also that you can also think of this bordism group with the letter on top, G, as a module of the bordism group without the letter. How is that? Well, you take a manifold with a G action, and you somehow do the cross product with a manifold with a trivial action, and you just simply take the new manifold, which is the product of the two, with the induced action. So this is the unitary bordism ring without G, and this is the equivariant one. So, and one is a module over the other. Now, so far, what I'm putting is a geometrical question in an algebraic setup, in some sense. I want to understand manifolds up to bordism, and I somehow package them into a ring. And that's what so whenever I say these rings, you should think of it of manifolds of some kind. So there is a very famous construction of Thom-Pontragin that somehow managed to bring this question about manifolds set up into an algebraic setting as a ring to be the homotopy groups of specific spaces. This is what is called the Thom-Pontragin construction. So the idea is to cook up manifolds as transversal intersection sets on a specific bundle. And the bundle in this is the universal bundle for rank n complex bundles. And so the idea to cook up manifolds, instead of having them abstractly, the manifolds will be zero sets of certain, or transversal intersections of manifold themselves, or zero set of sections of a bundle. So in this way, we translate an abstract problem to a place on which we live in a universe on which we can do transversal intersection. So what is this terminology? BUN is the classifying space of rank n complex bundles. You can think of it as the Grassmannian of n places in C infinity. And this is somehow the universal bundle itself. And as a bundle, I can do something that is called the Thom construction of the bundle. Namely, you take the disk bundle, namely all the vectors has dimension less than 1, and you just simply mod out by the vectors that has dimension 1. You simply take the disk bundle and you collapse all the spheres to a point. In the sense, you take a disk and you can collapse it to a point, you get a sphere, but now you do it on all the fibers, and the collapsing is just one point. That is what is called the Thom construction. So what is very important here is that the equivariant bordism ring, or the elements of dimension n, could be calculated, and that's what is really important about this theorem, as the stably homotopy groups, or let's call it like as the homotopy groups of these spaces, of these Thom spaces. So we have somehow translated a geometrical problem that was put algebraic into a calculation of homotopy groups. And somehow the question of calculating homotopy groups, it turns out to be easier than to calculating algebraically and abstractly these bordism groups. So I will focus only on this unitary case, and I will disregard a little bit the history. Namely, this started by somehow Thom calculating the unoriented bordism ring, and then the oriented, and then Milnor and Novikov somehow were the ones that brought the idea of studying the unitary ones. So, but I will focus on those ones. So it turns out that the bordism ring without any G action, this one that I'm pointing out here, as an algebra, as a ring, is simply a polynomial algebra on generators of dimension 2, 4, 6, and so on. But somehow one should think of this also algebraic, geometrically. And let me put it easier this way. When you tensor with the rationals, we can take the generators, the projective spaces. So let me explain this thing a little bit more simply. Any manifold with a unitary structure that I explained before, you may add it several times, and there is an n on which if you add it n times, there is a bordism with some sort of product of these ones. So any manifold somehow, no matter what it is, there's a bordism with products of projective spaces. And the invariant that determines this is the Chern numbers. So you have your manifold, you take the Chern classes, you integrate on the manifold on Chern classes until the degree is the appropriate one, and you take all those numbers. If all those numbers for two manifolds agree, the manifolds are cobordant in this sense. And these are the complete invariants due to this result of Milnor and Novikov. So whenever there is no group, there is a specific ring, and this is the coefficients of the theory. Well, when we have a GCW complex, we can construct what I just said before, manifolds living in X, and this becomes a generalized equivariant homology theory. So as any homology theory that you might imagine, like standard singular homology, well, this is another homology theory. Good. So there is also a homotopical version. So I just told you geometrically what it is and what is the relation with this construction of Thom and Pontragin regarding the homotopy groups. Well, there is a way to construct the same thing as I just said before, equivariantly. Namely, we just construct some universal space on which we have rank K bundles on which there is an action. So this is a universal space on which you may put any equivariant bundle on it. And you can do the same construction. This is the Thom construction, and you can do some sort of limit, as I just said before, but one has to be careful that one wants to take a limit over all representations. And let me explain what are this terminology. This is any representation. This is the sphere representation, namely the compactification at one point. This is space that I put here, and this is X. No matter what, this is somehow the homotopical version of the geometrical object that I just defined. The first thing that one would expect, let me put it here, is that these two things are isomorphic. So the point is that the Thom-Pontragin map, whenever there is no group, tells us that these two things are the same. The geometrical one or the homotopic one. But whenever you put a group, they become differently. And the reason is, one can do a simple calculation that, well, the geometrical one is only graded positively because all manifolds are positive. But on the right-hand side, there are elements of negative degree. And the simplest elements to construct is just simply taking irreducible representations of G whenever they don't have any fixed points beside the zero. And if you take the spheres and you take an appropriate map, they define classes of negative degree. So the right-hand side has negative degree, the left-hand side has not negative degree, so there is no way to expect that one is isomorphic to the other. One might expect that the map is injective. Why am I telling you this? Because on the right-hand side, we can do transversal intersection with a group. Whenever we have a group, we cannot easily do transversal intersection. We will have restrictions on codimensions. So on the left-hand side, we're not allowed abstractly to do transversal intersections. On the right-hand side, we can do transversal intersections, but the price to pay is that you have to put a lot of dimensions to be able to do them. So in this sense, the two are different, and understanding one will help the other, and vice versa. So, but as I told you, this is a homology theory, or let's forget that it's a homology theory. I want to know, this works? Well, I want to know how many manifolds are there with an action that are unitary up to bordism. The original question, but now with a group. So I know what it is, the answer whenever it's without a group. I know that the generators are the CPIs when it's rational coefficients, and there are some other generators constructed by Milnor hypersurfaces. The question is, what are in these cases? One would expect that this question is easy. I thought it was easy. But it turns out that it's highly non-trivial. So the point is that instead of understanding this object as a ring, which is even more complicated, we will simply understand it as a module over the bordism ring. So it's as a module over the algebra, polynomial algebra, generated by even dimensional variables. So we want to understand it as a module over that algebra. Well, this was started in the 70s, and it has been done one by one in the abelian case. So it was in the 70s, 71. Landweber showed it for cyclic groups. 2 years later for generally abelian P groups. Then it was with these two information, one can construct it for any abelian group, and later on in the 80s and in the 90s for compact abelian groups. Very little is known about the case whenever the group is not abelian. So, and the question is, let me explain what is this somehow information. What it's telling me here is that the whole information is located on the even dimensional part, namely any odd dimensional manifold that has an action of this group that is unitary bounds. Then that's part of what this information says. And moreover, there is no torsion. There is no manifold that if you add it several times, then it bounds. So because of somehow this, and because some small cases of non-abelian groups will show it works also, I decided, and this is just myself, decided to highlight this question in these proceedings, which was hidden, and I will show you where it was hidden in several papers. And I decided to give it a name, and because this name has already appeared in other cases, and I just decided to invent this conjecture as a conjecture, and I called it evenness conjecture for the equivariant unitary bordism groups. So somehow, the name of the conjecture says what it is. Well, fortunately, one doesn't have to say more. The title says everything. And what it says is simply that the G-equivariant bordism groups has to be a free module over the unitary bordism group. Well, for an Lie group, compact, let's say, let's hope. I don't know. I only know it for those cases that I just told you. And if we are able to show this conjecture, many things will somehow follow by themselves, because this is the information that is here is quite a lot. But as I told you, just imagine again that as in the bordism ring, there is no torsion classes. In this equivariant case, there should not be torsion classes either. Good. So this is what I want to talk about and to tell you how can one approach it, although it's not the unique approach. I'm just going to quote people that in the several years talk about this, and somehow to tell you just simply read them. So in the 80s, just quoted the following question, once under active study, has been dormant for several years, is the equivariant bordism ring always a free module on even dimensional generators? This is in the 80s. It seemed like it was a good question to pose. In 1996, then look at those words. In the light of this result, it is natural to conjecture, probably over-optimistically, that this module is free over the bordism ring. So somehow the energy has gone down and people started not to believe it. And then in 1997, Greenlees and May, a person very well known in the area of equivariant homotopy theory, well, says, well, we recall an old and probably false conjecture. Well, I put it in this terminology, but you could think it's the same thing. Is the equivariant bordism ring a free module on even dimensional generators? Well, it's already, in 1997, it became false. I don't know why, but it was, in 1996, was over-optimistically. And I put my somehow survey of these results in the archives, and Peter Landweber, which is also one of topologists from the 70s, read it and sent me an email saying, oh, congratulations that you brought to life an old problem that he thought was completely forgotten, which I found it quite amazing that still people somehow care about these things. And I still think that it's a problem that we should address because it's easy to state and it looks classical. So how it was done? And this, similar to the previous talk of Arthur Bartels, one of the tools that we have in our toolbox is to simply restrict the possibilities of isotropies on the manifold and to make somehow to build the equivariant object out of restricting the subgroups. We first go to the only subgroup, the only isotropy has to be trivial, and then we start adding isotropies until we have the whole picture. Some sort of spectral sequence in some sense. But so let me tell you what is the idea. So we take a family of subgroups, that is, take subgroups of a group, and you make this family to be closed under conjugation and under taking subgroups. You should think of a family as the possible isotropies that can appear in your manifold. That's how you should think of it. And we call a manifold free with respect to the family if all its isotropics lies in there. If the family it has only one group, which is the identity group, then being free in that family means that the action is free. Anyway, so if we only restrict to manifolds which have this specific isotropy, we call these bordism groups like this. So namely, I'm restricting the possible manifolds by determining the isotropy. But we can all do this also with a boundary. So we have two families of subgroups. One is smaller than the other. And we say that a manifold with boundary is f prime free if the isotropies in the interior are in F and the isotropies in the boundary is F prime. So we're controlling both isotropies in the manifold and in the boundary. And we call this the bordism groups of those families by this notation. It's some sort of simply it's like a homology of a pair, but in this way it's very geometrical. Now, the good thing is that this produces a long exact sequence that you can see here. So you have a manifold with less isotropy goes to a manifold with more isotropy, and then you can put boundaries, and once you have a boundary, you can take the boundary, and you are in the appropriate manifold. So it's the easiest way to get a long exact sequence, and you can now think the idea. The idea is that you go from a small family, you determine what goes on the pair, and you go one step up by the bigger family. And you do it step by step until you somehow reach the point on which you have all possible isotropy groups. It's not an easy task, but it's somehow, this way somehow constructing generators at each stage. This is somehow the approach that we'll do here. I want to point out again that a free action, so you take manifolds with a free action, is the same as having bordisms of the classifying space of manifolds with a free action. So in this case, it's an equivariant object. In the right-hand side is bordism of a space. So the idea is also to get the G on top and to bring it down. Because it's go down, it's a space, on top is more complicated. Good. So, and I want to just simply quote a statement or a result that we just cooked up with collaborators from Medellin and Bogotá, Andrés Ángel and José Manuel Gómez, which is the formula that you see here. Don't be scared of all these numbers and terminology. And I can explain you exactly what it means and just simply disregard all these symbols. I'll tell you what exactly it is. So I have a Lie group and I have a normal subgroup that is A. And I take the family that exactly differs by A. So in F is A, in F prime, A is not there. And it's the only group that is the difference. So that means that I'm allowed to have, I take a manifold, I'm allowed to have isotropy groups that are A in the interior, but not in the boundary, So I'm allowed to take fixed points by A. That's the whole point. So I have a manifold of this kind, and I take fixed points of A. And whenever I take fixed points of A, the manifold I get, which could be several connected components, that manifold has a free action of the quotient. So that's why there is a 1 here, so whatever I get has a free action. But I need to recall what is the normal bundle information. And the normal bundle information is classified by all these symbols. It doesn't matter. I'll tell you what are the symbols in a second. But these are all symbols that tell me exactly how I classify the information of the normal bundle. And the point is that to understand this is I need to calculate this part. What I want you to notice is that the complexity of the group is lower, but the price to pay is that I had to put some classifying spaces on the right. but the equivariant length is lower. So to explain what is on the right, and I need to go a little faster, I'll do this explanation on representations. The setup is I have a group A and a subgroup, a group G and a subgroup A that is normal, and I have this short exact sequence, and I want to somehow split a representation of G into pieces, but these pieces I want it to be somehow coherent with the information that I know of A. So I have a representation of G here, W, and I first split it using that W is a representation of A. So I take the irreducible representations of A, and I just simply use Schur's lemma, and I have this isomorphism. That's very easy and classical. But the point is that the right-hand side is a representation of G, and the left-hand side, a priori, is not. So I need to see how the G action on the right goes on the left. And precisely I want to know what happens with these pieces. The point is, and to make the story short, is that these pieces on here, this one and that one, both become projective representation of a specific subgroup of G. And it's easy somehow to detect what kind of projective representations there are. So I'll show you here in the next slide. Oh, too fast. Namely, I take a representation V0, I take the elements of the group that fix the isomorphism class, and therefore I have some matrices that make this equation hold. And what I do have is that if I have a representation of A, then what I get is a projective representation of this group G that fixes the representation V rho. And I can cook up a group by simply pulling it back from the map to the projective group, the projectivization. And this group here is now a central extension of the group G sub rho. The idea now is whenever I have here on this information is that on the right-hand side, I have a representation of this group, but on which the circle, there is a circle going on here, acts by multiplication. And on the other side, I have a representation of the same group, but now the circle is acting by multiplication with the inverse. Those multiplications cancel, and then I have a representation of the group G sub rho. So that leads me to this simple formula on representation. That is what I'm going to put forward in representation and equivariant K-theory and on bordism all the way to there to explain how we get this splitting. So simply, this is a representation of G sub rho, and you just induce it. This is always a finite index induction because of this fact here. So this is at the level of representations, and I need to speed up a little bit. So this is a representation. I can take the representation ring of a group, namely I take irreducible, I take simply representation, isomorphism class of representations, and I could just add them up and multiply them. And so what I have is, if I have representation of a group, and I take a normal subgroup that is A, I could split it in this way. Namely, these are representations of this group on which, these are projective representation of the group Q rho on which the representation is actually this central extension. So I just simply, it's like twisted representations in the language of the physicists of the 2000s. And the map is simply what we just saw here. But this splitting is pretty useful in all somehow cohomology theories that behave like this as K-theory. So, well, this is an example that I'm going to go a little bit fast on it. It doesn't matter because somehow I need to give you the point. I could do the same in K-theory. So in K-theory, I have a central extension of a group, and I can construct complex vector bundles on which Q acts on the base, but on which Q tilde acts on the total space, but with the condition that the circle has to act multiplication on the fibers. This was some sort of first definition of twisted K-theory in end of the 90s and 2000 that appeared somehow in physics. Anyway, so I could take those vector bundles, and with those vector bundles, I can define some twisted K-theory groups. So all this terminology here means that it's equivariant, but it's twisted, and the twisting is appearing in the group. It's not appearing anywhere else. So with that in mind, one can do the same splitting in K-theory. But the setup is, I have to take a space X on which the group that I'm focusing on, A, is acting trivially. And if you don't like that, take any space and take the A fixed point sets. It's somehow the same thing. If you do that, then this K-theory splits into these copies of twisted K-theories. And somehow with this information, one can somehow go back to K-theory, and one can explicitly determine third differentials in the spectral sequence. One can see what's happening in K-theory when one understands what's happening at the orbit space. And this is what's happening at the orbit space. Good. So I need to do that formula in like homotopy theoretically. I need to give you that formula at the level of classifying spaces. So that formula at the level of classified spaces requires all this symbology. The symbology, this is the universal space of such projective actions in some sense. So this is rank n complex bundles, that's the n. Q means that Q is acting on this space, but Q tilde is telling me that the group that is acting on the vector bundle is Q tilde with the property that the circle is acting by multiplication. So all the symbology is here. This is the universal space on which I have those twisted bundles. It's easy to construct. Simply take all representations of this central extension on which the circle is acting by multiplication, put infinitely many of them. So this is an infinite dimensional space. Take the Grassmannian of n planes, and that's the space. But this is somehow generic. You can construct it any other way. We can get the K theory out of these spaces when we just take a limit. And then I have a formula that for the people that know this type of classifying spaces may be clear. But just think of the formula that I had in representations. This is the coherent formula at the level of classifying spaces for vector bundles of a specific rank. So this is telling me this classifies G equivariant actions on spaces on which A acts trivially. And on the right-hand side, I have the splitting using these universal spaces, and this is the induction object. So it's somehow the same formula, but now put at the level of classifying space. Now that you've seen these spaces, I can go back to this theorem that I was just telling you about, and this is what goes on here. Simply take a manifold, take the fixed point set of A, look at the normal bundle. Now, A is acting on the normal bundle. Split it by the irreducible representations of A. Take homomorphisms from the irreducible representation to that normal bundle, split it into pieces, and this is telling me how these pieces split, because I just classify the map with here on the right. So it's a way to somehow to capture the information of the fixed point set and the normal information using these classifying spaces. So again, I wanted to calculate the bordism of pairs of families, and this becomes a bordism of something easier, quotes, of a specific topological space. This is the picture. So I should have more drawings, but this is an example of what's going on. I have a two-dimensional manifold with boundary with the action of the symmetric group on 3 letters. So you see the axis of, like the symmetries of the triangle. Now, what I want to know is I want to localize in the fixed point set of the group generated by B. The letter B, this is the group in here. So what I do is I take the fixed points of B, in this case are 2 points. I take the normal information, which is these 2 green objects, and the manifold that lies in here, that lies in the bordism group, has a manifold and boundary. It transports itself to the fixed point set, in this case is 2 points, but those 2 points are a normal bundle, and I classify them with the appropriate complex universal line bundle, which is BU1. So this, the manifold that I have in here, I send it to an object in the zero bordism group of BU1. And that's how it's happening. So, and I can do it for any other isotropy group in some sense. That's the map that it goes. So one could see that somehow, even though it looks very symbolic, this is a little easier. But let me tell you some examples. If I have a group that is abelian, and this is the reason why the evenness conjecture have worked out in the abelian case, is because whenever it's abelian, whatever is on the right-hand side, so I have a group that is abelian, I have a pairs of families which differ by only A, and I'm just using the formula of before, and I'm just simply telling you what is on the right-hand side. What happens is that because the group is abelian, all these somehow constructions split. And also, these twisted bundles are not twisted because there is no, from the group itself, you cannot get ever a central extension of these kinds that I told you before. So the elements that are here are not twisted, and they just simply become Grassmannians. So to calculate the left-hand side is a matter to calculate the bordism groups of a product of Grassmannians, which is somehow understood, with the complicated part of the bordism of a finite group, which is not easy to understand in the general case, but in the abelian case, we know a lot. Whenever we take another case is the case on which the pairs of families differ only by the total group. So the first family is all the subgroups, and the second family is all the subgroups besides G itself. So we are not allowing to have fixed point sets on the boundary of the whole group. So we fix points on the group, and what we get is that in these pairs of family, which is pretty useful and used, what we simply have is that it's isomorphic to the bordism group of Grassmannians. So then, and these Grassmannians are parameterized by the irreducible representations of, here in this case, G is A, no? And so we can reduce that problem into this one. In some cases, this is useful. But let me tell you 3 examples, and with that, I'm almost finished. So let's just think manifolds with actions of the group of P elements Z sub P. So this is what we should think of. And so what I'll do is I'll do this long exact sequence of Corner-Floyd with the only 2 families that there are, the family of everything and the family of the trivial group. There are only 2 subgroups, so it's easy. So what I have here is the Corner-Floyd long exact sequence, and I just translate it into what it becomes using the formulas of before. And it becomes into this long exact sequence of 4 terms. And I want to tell you that what I want to calculate is this symbol here. This is the bordism group of actions in general. And what I do get is this information. So if I know what is the bordism of free actions, and if I know what is the bordism of the Grassmannians, and if I know how the map goes, I can tell you what is this. And so the idea here is you take any manifold, and you simply take the fixed point set. You go here, and you classify the normal bundle. The normal bundle has P minus 1 irreducible representations. You classify them with this object in here. And then you take the boundary. The boundary has to be free. It's a free manifold, and that's it. So fortunately, for these cases, we know the structure of this as a module. We know the structure of this as a module. And we can go back here and tell, well, in this case, exactly, there are only classes in even dimensions. There are no classes in odd dimension. And it's a free module. And this is somehow how this works goes. This is in the easiest case, which is just one group. But in some other cases, it turns out that the other approaches are usable. In the case of torus, S1 to the n, it turns out that it's just enough to know the fixed point sets of the whole group, and then you know what is the bordism class. So the point in this case is, and it's only working for torus of this kind, you take any manifold in this group, take the fixed point sets of the whole group and the normal bundle information, and this map turns out to be injective. And because here on the right-hand side is bordism of Grassmannians, is everything even. And then there you are. This is a nice result of Tom Dick, and this is the way to get that the bordism of manifolds that are unitary with actions of the tori is only in even dimensions, and the rest is somehow 0. And in this case, the geometrical manifolds go injectively to the homotopical one. With my collaborators, we've been able to work a little bit on the first somehow non-trivial case for these gadgets, which is the quaternions group. So we've been able to show the conjecture for the dihedral groups whenever we have dihedral groups of 2p. We need that the numbers are relatively prime. The dihedral group of size 8 is a very difficult group. The quaternion group is a very difficult group. And so we have only able to say something whenever we take manifolds with the actions of the quaternions, but on which the fixed point sets of the center, which is a Z2 of Q8, has codimension at most 2. So we have to restrict to some very simple case of manifolds. Why? Because in that case, the normal bundle is somehow controlled by a specific group, and the specific group is this one. Is the only non-trivial central extension of C2 cross Z2. And the calculation depends on knowing what is the bordism group of the classifying space of that group. So what stops somehow the whole procedure to work is that in this procedure, one needs to know the bordism of basically the bordism of the classifying space of every finite group. Not only that, of any central extension, and etc. So somehow this procedure is like classifying groups or calculating the cohomology groups of all groups, which turns out to be very difficult. So one has to somehow to either change this somehow way to do it or take specific classes of groups that one can show that this happens. So just the last thing is one can localize on the fixed points of all subgroups. So take a manifold with an action of G and simply localize on the fixed point set of all of all subgroups. And this is what I have here. So take your manifold, take any subgroup, and simply localize or take the fixed point set, take the normal information, and take this is the information that lies here is the fixed point set and the normal bundle. And you simply do it for all subgroups, and we have a map, a morphism from the bordism ring to all this information. You should think this is letters, but this is the bordism, equivariant bordism, but here it's a bunch of Grassmannians. So because it's Grassmannians, this is not complicated in some sense. Well, in some sense. It turns out that if I tensor this map with the rationals, this becomes an isomorphism. So with the rational, the question is not complicated. With the rationals, basically the conjecture is true, namely rationally, the evenness conjecture holds, namely it's a free module over the bordism ring tensor the rationals. But the question that remains is what is the torsion, if any? What is the group that has a torsion? Or if no group has torsion? Or what is the manifold that destroys somehow this? What is the manifold and what is the group on which you cannot bound it, even though you may add copies of it? So simple consequences, if I had the evenness conjecture, and of course this is completely awkward because if one proves the evenness conjecture is because one proves what I will say, but you know how time is. Once you prove a theorem, then you think that the corollaries are exactly what you use to prove the theorem. Nevertheless, so if I show the evenness conjecture, then I know how to determine when a manifold with an action bounds or not. So I told you a long time ago, 45 years ago, somehow Pontragin told us what is the point. So you simply go and take a manifold and take the Chern classes and multiply them, integrate them in the manifold and give you some numbers. If all these numbers are 0, your manifold bounds. So the question is, what are the numerical invariants whenever you have an action? The same question. What are the integrals that I need to do that if everything is 0, then the manifold bounds? Well, if I have this inclusion here, then I know that what I do is I take the invariants on the right-hand side. These are bordisms of Grassmannians, or in other words, bordisms of manifolds with vector bundles on them, and I could just take the Chern classes of the manifold with the Chern classes of the bundle, multiply themselves all, integrate, and if everything is 0, then it would tell me that the manifold bounds. And another one, of course, which is you needed to prove the conjecture is the homology of a finite group is always torsion. The bordism of a finite group is always torsion besides the part of trivial actions. So that means that if you give me a non-trivial bordism class with which has a free action, which is torsion, if you send it as a manifold on which you have no restriction on the group, has to bound. Because if the conjecture is true, this is torsion free, the right-hand side is torsion free, so everything that is torsion has to simply goes to 0. So it will tell me if you have any manifold with a free action, you may somehow fill it with a manifold of one dimension more, but on which you don't control the action. This will be a consequence of that, but of course, as I tell you, to prove the evenness conjecture, one has to show first this. This is the kind of the last step that one needs to do. You need to fill all the manifolds with free actions. So just to end, you have 2 minutes. So I wanted somehow to tell you about a question that is open since the 1970s, that it was somehow studied for a while, and somehow I really don't know the reason why people stopped thinking about it. Perhaps didn't have the tools, perhaps didn't have this classification, perhaps it was too difficult, perhaps it was not interesting. I don't know. And so, but I found out that somehow we topologists, we talk about bordism theories, and I was very, somehow, not ashamed, but shocked that we didn't even know the coefficients of these bordism theories that we talk about, and we all do all these theorems from left to right, and we don't know what are the coefficients of the theory. Somehow we should try to calculate the coefficients. So we know it for all abelian groups. We know for certain simple groups as semi-direct products, because one can simply show, and the central extensions are not complicated. Little is known for other cases. I've done with my collaborators some calculations with the quaternions. We believe that the conjecture should hold for groups with periodic cohomology, because in those cases many properties with regards to the bordism group apply. To finish, this conjecture again has been open for many years, and it came to me, this problem coming from K-theory, I had done that decomposition that I told you in K-theory, and Ulrike Tillman, like a year and a half ago, asked me whether this equation that I wrote works for any other cohomology theory. So the other two equivariant cohomology theories that somehow we have around are the cohomotopy groups, equivariant, and the bordism ones. So I started to look at the bordism, and I was somehow shocked to find that we didn't know what are the coefficients. So I could not see whether the formula was true because we didn't know the coefficients, and I'm sure the formula will not hold the same way because the coefficients are more complicated. I believe, and this is my belief, that with the help of perhaps other people that have studied groups and actions from many other perspectives, from differential geometry, dynamical systems, perhaps they have a way to figure out what are these manifolds with these actions, because somehow whenever we do this, we have a specific manifolds with the specific actions that are the generators. It's not some random manifolds. We know exactly what they are. So if we have some sort of a big set of manifolds with actions that exist, perhaps one can somehow put them into the picture and say, oh, look, this is a generator. So perhaps people in other areas, or in homotopy theory with very, very somehow high-level tools have developed. As Soren is here, he's one of them. Perhaps we can solve this conjecture in the near future. Well, thank you very much for your attention, and thank you for coming.
So is there any question or comment?
Thank you for the talk. I'm guessing that in the late 90s, people became skeptical about this because of Igor Kryz's counterexample to a vaguely related, well, reminiscent conjecture about Morava K theory of finite groups. Now, is there actually any connection between those two, and is it worth looking at his counterexample group to see what's happening in these circumstances?
Good point, because the name that I put came from that. And somehow that's Morava K theory of BG. And somehow this is not BG. BG is there, but one has to bound everything that comes from BG. I've seen this example, and the group is so big, and I'm so, like, I'm in the dihedral groups, and so I don't know. Maybe that's the group that tells me the counterexample, but I have no clue how to calculate its bordism groups. So, but I don't know. Somehow the conjecture is there, but maybe, as Greenlees may say, it's false, but I don't know based on what. So I don't know. I don't know. But I know this example, but it's too big.
Well, I basically had the same question, so that's. I mean, but as you know, there were attempts to decrease. To find smaller counterexamples, but as far as I know, that they weren't successful. So,
I don't know. Somehow I've asked around, and Landweber didn't tell me. And
yeah, you didn't hear
but
because.
On the other hand, when one reads the papers and one reads between the lines, it seems that they had more examples on which these hold. It's written there. Oh, I've calculated SU2, and I've calculated, but it says that it holds for SU2, but you don't see it anywhere written. And also, we as a community have been a little sloppy in this issue because somehow you read one paper and the author says, oh, and the proof was incomplete in the other one, and then, oh, but I completed it. It's somehow a little awkward as the community has been, because it somehow is giving the idea that everybody is doing it incomplete, and so for some people it would be a place not to work, because if everybody says the other one is incomplete, then better not to work there, because it's too dangerous to use a result if everybody's incomplete.
Yeah, but this result is checked and sound, so...
No, I know. Some of them are true, but as I said, Comesaña himself in his paper in the Alaska issue, he says, and I've calculated the SU2 and all the dihedral groups, and they hold. Okay. So we believe you, or I don't know. So they've been calculated, you say. It's just they haven't been written. Okay.
Is there any other question? Okay, thank you, speaker.
Thank you very much. Thank you very much.